Hello viewers, welcome to the session on linear discriminant analysis in machine learning. Please make sure to watch all the prerequisite videos for your clear understanding and to make best use of it. When it comes to the definition of linear discriminant analysis or normal discriminant analysis, which is also known as discriminant function analysis, is a dimensionality reduction technique which is commonly used for classification problems. Here, from the n independent variables of a dataset, LDA extracts p independent variables which is less than or equal to n independent variable such that p separates the most of the classes of the dependent variable, and hence linear discriminant analysis is a supervised learning technique, and we are going to discuss this in the hands-on session also. The application of dimensionality reduction is that LDA is mainly used as a dimensionality reduction technique in various AI applications such as computer vision and image compression, and it is also used for finding the hidden patterns if the data has high dimensions. The applications of linear dimensional The application of linear discriminant analysis is mainly used as a dimensionality reduction technique in various AI applications such as computer vision and image compressions. And it also is used for finding hidden patterns if the data has high dimensions. Some fields where LDA is commonly used are finance, data mining, and psychology. So let's quickly look into the algorithm of linear discriminant analysis. The LDA can be achieved in 3 steps. The very first step is to calculate the separability between different classes, that is, the distance between the mean of different classes, and it is known as between class variance. And the next step is to calculate the distance between the mean and sample of each class, which is called the within class variance. And the third and final step is to construct the lower dimensional space whose objective is to maximize between class variance and minimize the within class variance. Now let's understand it more clearly. So whatever doubt you may be having will be clear right here. Let's take an example that we have two classes and we need to separate them efficiently. Classes can have multiple features, and using only a single feature to classify them may result in some overlapping. So we will keep on increasing the number of features for the proper classification. Consider this example. In the principal component analysis, we were finding this line where we can drop all these actual data points such that it can separate them. But you can see here there is the chances of overlapping as the red point is on the opposite side of the blue class. So in order to correct it and in order to improve it, we have LDA. And you can see in this example clearly that earlier, before LDA, you can see with the separation between the classes was very low, as many of the data points of this class were lying in the class of blue. So after LDA, you can see that it has given a good separation between each class. Finally, it's time for your favorite hands-on session on linear discriminant analysis in Python. So firstly, I'm importing all the important libraries, and then I'm going to load the same dataset that we were working on the principal component analysis, that is wine dataset. Let me load it once again and let me show you the dataset for your quick reference. See, it has 13 independent variables and one dependent variable which is dependent on this 13 independent variables, that is customer segment. And customer segment is having three discrete values, that is 1, 2 and 3. So after that, I am going to segregate my dataset into independent and dependent dataset. See, it has been executed successfully. The X is containing all the independent variables, all the 13 independent variables, and Y is our dependent variable. And now I'm going to split my data set into testing, training and testing set. For that I have defined that testing set should be 20%, which automatically means that we are training our model to 80% of the data set. See, after that, since here I can see that in the data in the independent data set there is a huge gap between the variables. See, in one variable we are having a value of about 107 and the another variable is containing 0.56. So to bring down this gap we are going to do feature scaling, that is standard scaling. So I'm executing. See, it has been executed successfully. Now this is the major chunk of code that we will need to understand here, that is linear discriminant analysis. From sklearn library I am using discriminant analysis module and importing linear discriminant analysis class. So I am creating the object of this linear discriminant analysis class and noted it as LDA. And from the previous example in the PCA we have seen that it has given n components as 2. Majority that is defining our dependent variable is only 2 components. So I have mentioned it 2 here. And as we have discussed in our theoretical slides that the linear discriminant analysis is a supervised learning, and hence here you can see that we are training both X-train, we are passing both X-train and Y-train as parameters, whereas PCA is our unsupervised learning where we were just passing the independent variables, whereas LDA is supervised learning and hence we are training our model with both X-train and Y-train. That is, dependent variable is dependent on the independent variable and hence it is a supervised learning. And then see, I'm just going to execute this chunk of code. See, it has been executed successfully. Now let's check our accuracy. First let me load the logistic regression for the same dataset. Further, I have called from sklearn library, I have used linear model and used logistic regression. We have already created video over this. Just we are going to predict our results. See, it has been executed successfully. This Y predict contains the values of the predictions that we have done from the X test. That is, this is our predicted value and Y test is our actual value. So let's now look into the confusion matrix. Let me execute this. See, in PCA it was around 97%, the confusion in the confusion matrix, and here you can see there is no error, so almost it is giving 100% accuracy. Let's quickly check into the accuracy score. See, it has been executed successfully and you can see the 100% accuracy right here. And lastly, let's visualize our code. So for that I am executing this visualization chunk of code. See, it has been executed successfully. There is no overlapping of one data point into the other set, so it's a good prediction of 100% accuracy. And as usual, I have included code snippet for your fast revision, so you can pause your video right here and can take screenshot of the same for your future reference. I hope this video proved fruitful to you and hope you have gained something extra than what you were knowing earlier. Thank you.